Hi, everyone. So in the last lecture, we started taking a look at the 4 new decomposition rules we're going to need to accommodate the complexities of what we've added to the language to form the language PL. And let me just remind you of what those rules were. We have not for all, we have the negation of universal decomposition, the negation of existential decomposition, universal decomposition, and existential decomposition. So what is the negation of universal decomposition tells us that if we have the negation of a universal quantification, we can push that negation sign through the quantifier. It pops out the other side and flips the quantity. Similarly, if we have the negation of an existential quantification, we can push that negation sign through and it flips the quantity. If we have a universal quantification, we can write down any instance at all, and these, by the way, we check because we've finished decomposing them. We can write down any substitution instance at all using any constant, and we do not check the universal quantification because there are, we never finish decomposing it because theoretically there are an infinite number of instances. And we'll see that we're going to have occasion at times to go back and put yet another instance of a universal quantification on the branch. It is reinstantiate a universal quantification. Existential decomposition tells us that if we see an existential quantification on a branch, we can write down an instance of it, but your instantiating constant must be new. And we looked at an example that I think illustrated why it is the case that it must be new. Okay, so what I want to do now, if I can find my notes here. So what I want to do now is something a little bit different. I'm going to start with an argument in English, and just so that you can kind of, get a sense of what you can do with these tools. I'm going to start with an argument in English, and then I'm going to translate it into PL, and then we will test its translation into PL for quantificational validity, and then make an inference about what the validity of the argument in English is. Okay, so the argument that I want to look at is Holmes, Sherlock Holmes that is, if anyone can trap Moriarty, Holmes cannot. Therefore, no one can. So we want to translate this into PL. We haven't done any translations in a while. We want to translate this into PL and then test the translation for quantificational validity. So how do we translate this? Well, we're going to need a dictionary. We're going to have, say, our universe of discourse be people. We're going to need a two-place predicate for trapping. And we're going to need a constant for Holmes. And that'll do it, right? So how are we going to translate this? Holmes, if anyone can trap Moriarty, that is, if anyone can trap Moriarty, Holmes can. And there are actually 2 ways in which we can translate that. This is an example of that funny equivalence on page 302. It could be for all x, if x can trap, oops, we also need, we need another constant for Moriarty. If Holmes, if anyone, for all x, if x can trap Moriarty, then Holmes can trap Moriarty. So that's one way of translating the sentence. And it's equivalent to, notice how the consequent here doesn't have an occurrence of x. So if we wanted to confine the quantifier to just the antecedent, it becomes this. Okay, I keep reminding you of that funny equivalence, but here's a nice example of it. And you should be able to see that these are equivalent, because in English they sound like they are. Everybody is such that if that person can trap Moriarty, Holmes can trap Moriarty. If there is at least one person who can trap Moriarty, then Holmes can trap Moriarty. Okay? Okay. The second premise is Holmes cannot. What does that mean? Holmes cannot trap Moriarty. It's not the case that Holmes can trap Moriarty. And then the conclusion is no one can would be there doesn't exist anybody who can trap Moriarty. So let's use this. The second, these two are equivalent, but just for the sake of the tree that we're going to do, we have to pick one. So let's pick the second one. Okay. So we're going to do a tree, and remember, how do you test an argument for validity using the tree method? You do a tree for the set that has the premises and the negation of the conclusion. So the premises are, if there's at least one person who can trap Moriarty, then Holmes can trap Moriarty. Secondly, it's not the case that Holmes can trap Moriarty. And then finally, the negation of the conclusion. That is, it's not the case that there isn't somebody who can trap Moriarty. Okay, so now I'm going to construct this tree. What shall I do first? I'm going to get rid of that double negation on line 3. So I'm going to apply double negation decomposition to line 3, yielding this. All right. Now, what have we got? We've got an existential quantification on line 4, and we have a branching rule that applies to line number 1. When I apply conditional decomposition to line number 1, I'm going to have the negation of an existential decomposition on the left, and then an atomic sentence on the right. So I wanted to say something about strategies, and so let me scroll down. I'm going to put these strategies, and then I'll come back to because what we're trying to decide is, should we do this one first, or should we do that one first? Which of those should we decompose first? Well, the strategies that we developed, I'll just put them the same. The strategies that we developed back in SL, the tree method for sentential logic, still apply. So you want to apply non-branching rules first. Okay, and also remember we had another strategy, which is choose a rule that results in a branch closing. So if you can apply a decomposition rule that closes a branch, do that. I'm just reviewing the strategies that we had before. Okay, another strategy that's just that we're going to have to think about with respect to predicate logic is, if we have a choice of applying an existential decomposition or a universal decomposition, it makes sense to apply existential decomposition before you apply universal decomposition. And why is that? And the reason I'm stopping to talk about this is that we're faced with that choice here. Now, I'm looking a couple of moves ahead. On line number 4, I've got an existential quantification. And we know that the existential decomposition rule comes with this restriction that your choice of names that you instantiate with must be new. You've got to instantiate with a new name. So there's some restrictions on that. When I decompose line number 1, it's going to branch, and on the left I'm going to have the negation of an existential quantification, which is going to revert to a universal quantification when I apply negation existential decomposition. And so that's going to be a universal. So why would I apply existential before I apply universal? Because I have greater freedom in my instantiating constant if I apply existential first, because I can always apply a universal using any constant that I like. Okay, and we'll see more examples of that. So that's an important strategy. And then another strategy that I mentioned in the last lecture is when applying universal decomposition, when you apply universal decomposition, there's never a reason to choose a new name. And we talked about why that's the case in the last lecture. So when applying universal decomposition, choose an instance whose constant already occurs on the branch. And why is that? Remember, it's because introducing a new name is never going to get something to close. And so if you can't remember that, go back and take a look at the example I gave in the last lecture. Okay, so those are the strategies that that we have for trees for PL. So we've added these two strategies, and we'll see plenty of examples of using them. Okay, so now what should I do? Why don't I start the tree? Should I start the tree over again? No, I think I'll just erase this. You've seen it. And then just continue the tree. Okay, so I'll leave the two new ones there. Maybe I'll have enough room. Okay, so because of this strategy, this first new strategy we've got, I'm going to decompose line number 4 before I decompose line number 1. So on line number 5, I'm going to apply existential decomposition to line 4. I can't use H and I can't use M because this says there's at least one person who can trap Moriarty. And we can't just assume it's Moriarty who traps himself. We can't assume that Holmes can trap Moriarty. This just says there's at least one person who can trap Moriarty. So we have to choose an arbitrary name. I'm going to choose the alphabetically first available name, which is A. Let's call that guy who can trap Moriarty A. And we get that from 4 by existential decomposition. And now I'm going to go ahead and decompose line number 1, which is going to branch. And I'm going to have the negation of the antecedent on the left and the consequent on the right. And I get that from 1 by conditional decomposition. And look what I've got here. So whenever you decompose something, just like with truth functional logic, you want to look up the branch and see whether the branch closes. I've got Holmes can trap Moriarty here, but on line number 2, I have Holmes cannot trap Moriarty. So I have an atomic and its negation, so that branch closes. Okay, good. Let's take a look now at the left branch. On the left branch, we've got the negation of an existential. We're going to apply the appropriate rule to that, push that negation sign through. Check that, and I get that from 6 by negation existential decomposition. And now I'm going to apply universal decomposition to line number 7. Now, it certainly doesn't make any sense to introduce a new constant, right? Thinking about this rule. This says everybody cannot trap Moriarty, right? Everybody is such that that person cannot trap Moriarty. It doesn't make sense to say, oh, well, B can't trap Moriarty or C can't trap Moriarty. We should use a name that already appears on the branch. And I'm also going to think about sort of strategically, which name does it make sense to use? Well, look at line number 5. I've got that A can trap Moriarty. So if I write down the instance using A as my instantiating constant, it's not the case that A can trap Moriarty. That's a negation sign. Sorry about that. Then I've got on line 8, A cannot trap Moriarty. And on line 5, I have A can trap Moriarty. So that closes. And that, by the way, line 8 I got from line 7 by universal decomposition, which I do not check. Okay? So the tree closes. So the argument is quantificationally valid. Because what does this show? This shows that there is no interpretation that makes the premises of the argument true and the conclusion of the argument false. It rules out an interpretation that does that. So the argument is quantificationally valid, and I think it's safe to infer that the argument that is the translation of is a valid argument. Okay, well that was kind of fun. Let's go ahead and do another example. Let's do this one. All right. Suppose that we have a set that has just one member, and that sentence is, there is an X that's both F and G, horseshoe, everything is F and G. So it says if there's at least one thing that's F and G, well then everything is F and G. If there's at least one thing in the universe that's F and G, well then everything in the universe is both F and G. And we want to see whether the set that has this as its only member is quantificationally consistent. Okay, well let's think, before we do the tree, let's think about the sentence for a moment. The antecedent, okay, so suppose there were an interpretation that makes the antecedent true. There's at least one thing that's F and G. Well, gee, how could it be that, if there's at least one thing that's F and G, well, it doesn't follow that everything is F and G, but if there's only one thing in the universe and that thing is both F and G, well then everything, if there's only one thing, then everything in the universe is both F and G. So this is going to be, we could come up with an interpretation that has just one thing in the universe, put it into both the extension of F and the extension of G, then both the antecedent and the consequent of this turns out to be true. So that's one way that an interpretation could make it true. Another way an interpretation could make it true is if there isn't anything that's both F and G, and then the whole thing's true by falsity of the antecedent. So we're going in with a very strong hunch that there is at least one interpretation that makes this true, but let's do the tree. Okay? So we expect this tree to be open, to have at least one open branch. Completed open branch. We're going to have to think about what that means in a moment. Completed, but we'll get to that. So this is going to branch because I'm going to apply conditional decomposition to it. And so on the left I'm going to have, it's not the case that there's something that's F and G. And on the right I'm going to have everything is F and G. And I get that from 1 by conditional decomposition. Let me do the left-hand side first. The rule that applies to line number 2 is negation existential decomposition. So I'm going to push that negation sign through. It flips the quantity. I talked about this when we were doing trees for sentential logic. I'll say it again because it's even more important to keep this in mind for predicate logic. There is always a unique rule that applies to a sentence. There's exactly one rule that applies to the sentence, and that's going to be determined by the main operator of the sentence. So you can't go fussing around with the innards of a sentence. First, you've got to apply the one and only one rule that applies to it. And in the case of line number 2 on the left, it's negation existential decomposition. Okay, now I'm going to apply universal decomposition to line 3, and I can use, because it's universal decomposition, any constant I like. I'm just going to use the alphabetically first one, which is A, and I'm going to get, it's not the case that FA and GA. I meant to check that, not line number 3. Sorry, put it in the wrong place. Because I'm not going to check line number 3 because it's a universal quantification. And so I get that from 3 by universal decomposition. And now I'm going to apply good old negation conjunction decomposition, which branches. So I have not FA on the left and not GA on the right. And I get that from 3 by negation conjunction decomposition. And what do I do now on the left-hand side? Are those branches completed and open? Well, we're going to talk about that in a moment. But our intuition is that, and the reason that the question even arises is if you take a look at line number 3, we have this universal quantification. We haven't checked it, indicating that it's not completely decomposed, because we could always decompose it again using B or C or D or any constant that we like. But we have a very strong hunch, I hope an insight, that no matter what instance of line number 3 I were to write down on the left-hand side, I'm never going to get these branches to close, right? I'm never going to get a constant, an atomic and its negation on that branch. So we'll come back and talk about that in a minute. But I think now I hope you feel fairly confident that we can leave the left-hand side of the branch with this intuition that it's not going to close. And now I'm going to look at the right-hand side of the branch, which is a universal quantification. Note that on the right-hand side of the branch, there is no constant yet, right? So when I apply, because over here, A is on the left-hand side, A is only on the left-hand side, it's not on the right-hand side. So when I apply universal decomposition to the left-hand side, I'm just going to use the alphabetically first thing that's available, which is A, and I'm going to get FA and GA, and I get that from line number 2 by universal decomposition. I don't check it. And then I have FA and GA, which I get by applying conjunction decomposition to line number 6. And now, once again, we could, of course, reinstantiate line number 2, write down yet another instance of line number 2, FB and GB, FC and GC, FD and GD, and so on. But we don't feel like we should do that or need to do that because we recognize that we're not going to get this branch to close no matter what instance or how many instances of line number 2 we write down. So I feel pretty comfortable, and I hope you do, sort of abandoning the tree at this point and saying this tree is open. Okay, and as I said, we'll talk about this in a more rigorous way in a moment. So I mentioned in the last lecture that when we've got an open branch, we can take a look at the literals that appear on that branch and construct an interpretation suggested by those literals. Why is that the case? Remember that what we're doing when we construct, this cat is driving me crazy, what we're doing when we're constructing a tree for a set of sentences is we're wondering, is there at least one interpretation that makes these set members true? And in the case of this tree, we're asking ourselves, is there at least one interpretation that makes line number 1 true? And what we're doing is we're doing a search for such an interpretation, and in a way if there is an interpretation, we're kind of constructing it as we do the tree. So if we take a look at line number 1, we're saying, okay, suppose there were an interpretation that made line number 1 true. Well, there are 2 ways that could happen. It could either make the antecedent false, or it could make the consequent true, right? And when we first looked at this sentence, we thought about just that. Oh, well, yeah, line number 1 could be true in an interpretation if there's nothing in the universe that's both F and G. Well, that's what's going on the left-hand side. And so then we sort of carried out, like, okay, so suppose there weren't anything that's both F and G. Well, then here's a scenario, right? And alternatively, suppose everything is F and G. Well, then here's a scenario. So what we're doing is we're kind of, in a sense, looking at what an interpretation would look like, a bare bones interpretation would look like that would make the set member true. And here's where the method that I introduced for constructing interpretations back when we were looking at Chapter 8 puts you in a very good position to be able to do this now. Because what we're going to do, and I suggested this in the last lecture, is we're going to look at the open branches, collect the interpretations that we can from the open branches, and see what, collect the, literals that we can from the open branch, and then see what interpretations they suggest. So I'm going to do this one by one, okay? We've got 3 open branches. We've got that one's open, and that one's open. And let's take a look at what we can get from this open branch. The only literal on the branch is not FA. Well, what does that suggest? That suggests a universe of discourse that's got one thing in it. By the way, A does not appear in our set member. We don't, in this interpretation that makes the set member true, we don't need to give a referent for A because A was generated by applying decomposition rules. It's not part of the set members, okay? But this literal tells us what an interpretation might look like that makes it true. It's what it suggests is a universe of discourse that has one thing in it. I'm going to think of A as naming that thing. A is naming one. And what it tells us is that don't put that thing into the extension of A. Well, if that's the only thing in the universe and it's not in the extension of A, then not in the extension of F, don't put it into the extension of F. If there's only one thing in the universe and we don't put it in the extension of F, well, then the extension of F is empty. Now, neither G nor its negation, we don't have anything about A being in or out of G on the left-hand side, so we can do whatever we like. As long as F is empty, this literal tells us the interpretation will do the job. But let's just make it be empty, okay? Now, let's look at this interpretation. What's the status, what's the truth value of the antecedent? There's something that's F and G. Well, that's going to be false, right? So if that's false, well, then the whole thing is true. So that interpretation does the job. And this interpretation, this literal over here, let me make it a different color. If we take a look at this literal, it's going to suggest, once again, a universe of discourse with one thing in it, and we don't put it into the extension of G. It doesn't tell us anything about F, so let's just leave F empty as we did before, and we have the same interpretation as we had there. Okay. Finally, the right-hand open branch, we've got the literals we've got there are FA and GA. So this once again suggests an interpretation that's got one thing in the universe, because only one constant appears on the open branch. And it tells us, put it into the extension of F, and also put it in, that's what this tells us, right? And also put it into the extension of G. That's what this literal tells us. And so that's the interpretation that the right-hand branch tells us, suggests to us. And let's go back and take a look at whether it works. There's one thing in the universe, and it's both in the extension of F and G, and so that turns out to be true, right? But so does this. If there's only one thing in the universe, and it's both in the extension of F and G, well, then everything is an extension of F and G, so that's true. So the whole conditional is true. So if you got a good grip on these abstract interpretations, it puts you in a very good position to be able to do what I just did and understand what you're doing, which was another reason that I introduced that method back in Chapter 8. And judging from the quizzes that I looked at, it looks like most people really did understand how to construct these interpretations. Okay, so yes, the set is quantificationally, the set that has line number 1 as its only member is quantificationally consistent. Moreover, the open branches gave us, a couple of interpretations that do the job. So this is kind of cool. It's kind of fun. So I want to think about this theoretical thing that I mentioned when we sort of stopped the tree, and I said, over here on the right-hand side, there's really no reason to write down another instance of line number 3, and over here, there's really no instance to write down another instance of line number 2 on the right-hand side. And so it raises this really important question. What do we mean by a completed open branch? Now, back in SL, we knew exactly what a completed open branch means. Namely, everything that's decomposable has been decomposed, and the branch is open. But there's this complication now, because if you've got a universal quantification, you never finish decomposing it. So, at what point can you say this branch is completed, even though I could theoretically write down more instances of a universal quantification? Let's look at an example. I think you're probably already formulating a hunch about what the criteria will be from the tree that we just did. But I don't like the yellow. Let's do an example. Suppose the set has as members these two sentences. If there's something that's G, then everything in the universe bears F to B. Okay, the main operator there is the horseshoe. Okay, if there's something that's G, then everything in the universe bears F to B. Well, that's kind of a weird sentence. And then the second sentence is there is at least one thing that fails to bear F to B. Okay. So if the set has these two members, is this set quantificationally consistent? Before I do the tree, let's think about it for a minute. If there is something that fails to bear F to B, well then this is going to be false, right? It's not the case that everything bears F to B. So then this would have to be false, but that's fine. So if this is true on an interpretation, well then that's automatically going to be false, but it's not hard to find an interpretation that also falsifies that. So I'm going into this tree with a hunch that these two sentences do form a consistent set. Let's go ahead. It's always nice to think about the problem before you just jump in and do it, because you might learn something along the way. Maybe your hunch is right, makes you feel good. Maybe your hunch is wrong, and you'll learn something. Okay, so the tree that I'm going to construct to test the set for consistency is this. I'm going to have as set members that and that. And what I'm going into this is thinking that, yeah, these form a consistent set, and I think my interpretation is going to be such that the extension of G is empty. There isn't anything that's in the extension of G, making the antecedent false. But there is at least one thing that doesn't bear F to whatever it is that B names. Okay, so let's do the tree. Now, what do I do first? Do I decompose line number 1 first, or do I decompose line number 2 first? On line number 2, I've got an existential quantification. On line number 1, I've got a conditional. A branching rule applies to line number 1. A non-branching rule applies to line number 2. We're going to apply existential decomposition to line 2 first. I have to choose a name that doesn't occur on the branch, and A is up for grabs, so I'm going to use it. I can't use B, right? This says there's at least one thing that doesn't bear F to B. Well, I can't call it B, I'm going to call it A. And I check that, and I get that from 2 by existential decomposition. And now I'm going to go ahead and apply conditional decomposition to line number 1, and I have the negation of the antecedent on the left and the consequent on the right. And I get that from 1 by conditional decomposition. And now I'm going to deal with I was going to deal with the left-hand side first, but the right-hand side is calling out to me, because what it says is that everything bears F to B, but line number 3 says A doesn't bear F to B. So I just can't resist this. If I use as my instantiating constant when I apply universal decomposition on the right-hand side, I can get FAB, and I get that from 4 by universal decomposition. And look what I've got, FAB and not FAB, and that closes. Okay, so I've got a closed branch. Let's go back to the left-hand side now. I've got the negation of an existential quantification. I'm going to apply negation existential decomposition to it, pushing that negation sign through, flipping the quantifier, and I have 4 negation existential decomposition. And now on line 6, I've got a universal quantification. Okay, remember the strategies that we were talking about? Where'd they go? Come back here. When applying universal decomposition, choose an instance whose constant already occurs on the branch. Well, A and B both are on that branch. Which one shall I use? Well, I want to make sure that I've done everything I possibly can do to close this branch, and it still hasn't closed. If I do every single thing I can do that might close the branch and the branch is still open, then I feel comfortable saying I've completed the branch and the tree is done. So the way in which I'm going to feel comfortable saying I've done everything possible and the branch is still open is by writing down both instances of line number 6, that is, using both of the constants that appear. So another way to think about this is what I'm doing when I'm constructing a tree is I'm wondering, is there an interpretation that makes these two true? Well, if there were, well, then it would have to make something like that true, and then it would have to make this true. So the interpretation that I've got in mind so far on line number 3 has two things in the universe, and then on line number 6, I'm saying everything in the universe is out of the extension of G. So in this interpretation that I'm kind of constructing over here, there are two things in it. So I have to say that A is not in G and B is not in G. And this branch is still open, right? So, and I get both of those from line number 6 by universal decomposition. So here's an example where we did go back and reinstantiate. First we wrote down one instance of line number 6, and then we wrote down another instance of line number 6. And the reason for that is, this little interpretation that we're kind of building as we construct the tree has, two things, the thing that A names and the thing that B names in the universe of discourse. And this says that everything in the universe is not G. Well, in particular, A is not G and B is not G. But this branch is still open. So I feel comfortable saying this is a completed open tree. It has a completed open branch. And I hope you share that intuition. So from this intuition, I'm going to give you sort of the rigorous criteria for what a completed open branch is in trees for PL. Okay? So this has one closed branch and it has one open branch, which theoretically, right, could go on and on and on. We could write down not GC, not GD, not GE. This could go on and on. But it's clear that no matter what substitution instance that we write down, we're never going to get that branch to close. Moreover, we've added the instances where using all of the constants that appear higher up on that branch. So we've done everything that we can do, and there's just no reason to write down any more instances of it. Okay, so the answer to our question, what do we mean by a completed open branch? Okay, first of all, it's finite. Oh, why is she saying it's finite? Because infinite branches exist. I mean, you can imagine this one going on forever, right? But we're going to actually be talking about trees that really do have infinite branches in a while. It's finite, and this is our definition of completed open branch. It's finite, and each sentence on the branch is either a literal, that is an atomic or the negation of atomic, or it's been decomposed. And it's not a universal, and it's not a universal quantification. That is, everything that's not a universal decomposition, quantification, has been decomposed. Okay? So in this case, that's been decomposed, that's been decomposed, but oops, we're going to have a clause concerning universal quantifications. Okay? And then secondly, or maybe, yeah, not secondly, but I'm going to continue this criterion. Okay, so it's finite and each sentence is a literal, or it's been decomposed and it's not a universal quantification. I'll just add it this way. Or it is a universal quantification, so of the form, say, for all x, blah, 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 such that you've written down each instance of it using the constants that appear higher up on the branch. Let me put it this way. So if it is a universal quantification of the form, for all x, blah, 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 then the sentence on the branch is such that the instance where you've put in a for x occurs on, I'm trying to do this in a rigorous way, and then I'll explain it a little less formally, on the branch for each constant. Of course, this is in the text. That occurs on the branch. Okay? So what do I mean by that? Why do I think that this branch over on the left is a completed open branch? Well, first of all, so far it's finite, right? Everything that's not a universal quantification has been decomposed, right? That's been decomposed, that's been decomposed, that's been decomposed. And if it's a universal quantification, then I've decomposed it using each of the constants that appears on that branch. So I have not GA and not GB. And that's what this is, what this says. And the second criterion is universal decomposition has been applied at least once. So you can't say, so like in this one you might say, oh, I don't think that applying universal decomposition to line 6 is going to get this thing to close, so I'm just going to stop it right here. Well, this criterion tells you, no, you can't do that. If you've got a universal quantification, you've got to decompose it at least once. And why is that the case? Well, I mean, like, you might be smart enough to recognize that no instance of line number 6 is going to get this thing to branch. But remember, we talked about the tree method for sentential logic not being as clever as you are. Similarly, the tree method for predicate logic isn't as clever as you are. Or you might have a tree that's really complicated and you don't see that, oh, this is the instance that I could write down that's going to get this thing to close. You might just miss it, right? So here's an example of why it would be crucial to apply universal decomposition at least once. So suppose your set member were something like, I don't know, suppose the set just had as member that. And so you do a tree for it. So your set member in your tree is line number 1. And then I apply negation existential, and I get that. Whoops. I forgot the negation sign. And I say, okay, this is a completed open branch. I'm done. But look, this is a tree that should close. This says there isn't anything in the universe that's F or not F. Right? How could that possibly be true on an interpretation? So you've got to apply it at least once, so you end up with not FA or not FA, and I get that from 2 by universal decomposition, and then I get, when I apply negation disjunction decomposition, I get not FA and not FA, and I get that from 3 by negation, disjunction decomposition, and then I get FA by double negation decomposition, and that's going to close, right? Not FA and FA. So you've got to apply universal decomposition at least once. If we had abandoned it here, saying, oh, that's open, there's no literal, no atomic and its negation on it, you'd be wrong, right? So you've got to apply universal decomposition at least once. Okay, and that's why I feel confident saying that this branch over here was a completed open branch. And back to the tree that we did initially, or secondarily, this was after the Holmes example. At this point, I was comfortable saying that this was a completed open branch and this is a completed open branch, because note that I have satisfied the criteria. I've applied universal decomposition at least once to line number 3, and I've applied it using each of the constants, although there is no constant. I've got at least one, right? I can't just stop here. There was no constant. Okay, we will see examples of this, lots more examples of this as we continue. Let's see, I'm trying to decide what to do next. And I'm thinking maybe that is enough for this lecture and for this module. So in this module, what have we done? We've done some more examples of interpretations. We talked about equivalence, we talked about entailment, validity, and we've also talked about so we've done some more interpretations, more complex ones, talking about other quantificational properties. So testing or demonstrating that sentences or sets of sentences do or don't have certain properties. And we've talked about interpretations or semantics for PL with identity, and we've started the tree method. And we've done a bunch of examples using the tree method. We have the 4 new rules. We've talked about a few theoretical matters. We've talked about strategies, and we've talked about what it means for an open branch to be a completed open branch. Back to the strategies that we were talking about. We had the old strategies and these 2 new strategies. Just as with the trees for sentential logic, if you don't think strategically when you construct trees for predicate logic, if you make sure that you've satisfied the criteria for an open branch being a completed open branch, well, then eventually you're going to get the right answer. But in trees for predicate logic, I suspect you're already starting to see that it's more important to think strategically, because these trees could get really pretty complicated if you don't, apply universal decomposition or existential before universal, and you start choosing constants that don't already appear on the branch. Things could get, unnecessarily complicated. So try to think strategically when you do these. So we've talked about strategies, and we worked through some fairly simple examples. And we talked a little bit about some theoretical stuff. Okay, so that's the kind of thing that will be on the quiz on Friday. And I'm going to stop here. Bye-bye for now.